Perfect. Okay, so we're going to continue our walkthrough on Shell Lab. So last class, we left off on trace 7, and my intent to show off trace 7 was to show how we could go ahead and kind of capture those signals and print them out right away. And I was having a little bit of issue with that. And what I should have done was just kind of problem with real-time coding endeavors is I needed to comment out my kill function, right? Because I was transmitting that to another part of my code. And so there I wasn't doing my printouts. But if you wanted to play around with that, which we don't have to, we have the appropriate implementation already, I would have commented out my kill function, which allows that communication from one process to another, which is the entire point of you doing the signal handling that we were doing for trace 7. Of course, when we completed trace 7, we left off on trace 8. But what you're going to see is that trace 8 is where we forward our interrupt signal only to our foreground jobs. Well, we were using a helper function that we get our job from the foreground, right? Like, so that we've already implemented that constraint. So there's no discrepancy between our current output. If I were to test this right away to see how does my tiny shell compare to the reference shell, well, if I implemented trace 7, we should automatically get through trace 8. I can't think of a good way to implement trace 7 without trace 8. So I'd be interested if you can find a way that makes sense. So let's make sure that we are starting off in the same space here. Let me jump into here, into Shell Lab. And here, let me open terminal. What do we have here? Let's make sure we have everything. Perfect. And before we start looking at trace 9, let's just make sure that our first 8 traces are working the way we expect them to. So I'm just going to go ahead and run our application, check tiny shell, a Python script. And so yes, trace 1, ages ago, trace 2, trace 3. Trace 4. You can see as we get deeper into the traces, it just takes longer for us to sit through and watch as our code gets evaluates, although it is a nice feeling, right, to see all the positive points accrue. Trace 5. Trace 7. And because we implemented trace 7, we get trace 8. And here we should fail on trace 9. And so we'll examine why. We'll take a look at the trace like we have been. Perfect. So we are right where we expect us to be on. So let me clear that. Okay, so let's jump over to the slides. Jump past this. We passed that. So now we're on to trace 9. In trace 9, our goal is to go ahead and forward our stop signal only to our foreground jobs. And so here we can see if we look at the directives inside of the trace, we have a call to do a mySpin for 4 seconds as a background process, as a background job. We have mySpin for 5 seconds as a foreground job. We're going to call sleep for 2 seconds from our driver, from our tester application, and then we're going to send a stop signal to the current foreground process. And then we're going to list the jobs that result from stopping that. And so if we take a look at the expected output from our reference test, and we'll ensure this by actually testing this ourselves, but we can compare our expected output to the output that we should likely get based off of our current implementation. So here we're going to echo that header comment. We're going to print this particular job 1, stats. Then we're going to print jobs 2 stats. And notice jobs 2 stats are going to print out as stopped by a particular signal, signal 20. Then we're going to print out the jobs. And so we'll see that we have 2 jobs, one that is running, the MySpin job, that is a background job. And we're going to see that one of the jobs has been stopped because we sent a signal for it to stop. And that's going to be the foreground job that we are trying to run for 5 seconds. Now, before I implement anything up to this point, and if I run my test, what we should see here is we will go ahead and get the echo of our header comments. I think eventually I'm just going to drop that first one. Like, we should always get that at this point. And then we're going to print the first job, that background job, because that's a printout that happens when we first launch a background job. But notice, then we're not going to do any additional printout after that. We're not going to have this printout to our shell to let us know that we've sent a signal to stop a job. And then when we do our job signal, we're not even going to, I don't think we even get jobs to even post anything. So let's take a look here. And let's run this. So let's make the reference test 9. Yeah, that's exactly stopped, running, stopped. Yeah, that's exactly what we just saw. And now let me do this with our tiny shell. And we get the comment header. We get this first. And then we get nothing else after that. Okay. So let's the obvious thing we're going to have to implement. We know that there's 3 signal handler functions that are part of our tiny shell that are currently stubbed out. And we've touched upon 2 of them already, right? So I think we touched, did we touch upon just one, the interrupt? Yeah. Okay. So now we're going to touch the second one, the stop signal handler. And so the general process by which we're going to handle this is we're going to retrieve the process ID of the current foreground job from the job list, pretty similar to what we did last time, right, with the interrupt signal. And we'll see if a foreground job does indeed exist, we're going to use that kill function so we can send that stop signal to suspend it. And clearly, the actions for this particular trace are going to be all new. We're not refactoring or adding to a function that we've touched before. So this is going to be all new code inside of our signal handler, our stop signal handler. And of course, the reason that we want to change this is to comply with not only trace 9, but to ensure that our tiny shell can be responsive to stop signals just like any other Unix-based system should be able to do. So we're trying to build something that's as lightweight, toy-like compliant as possible to understand what's happening underneath the hood here. Okay. So some of the key functions, we're going to use kill again, because kill allows us to send a signal to a process or a group of processes to either terminate, suspend, or otherwise cause a signal to continue. We're also going to use the the foreground process ID function, which is a helper function inside of our tiny shell. And that's going to retrieve the PID of the current foreground process, or 0 if there's no foreground job. So again, these are the same functions we use in trace 7. We will see it's going to be a very similar process. We've already seen the kill function. We're just going to move on. We just realized this kill function is a very powerful and useful system call for us to send messages to our processes. And the messages that we're sending are like status updates, these signals. And of course, we've already seen this. I don't want to spend too much time re-looking at the code itself, but we can just know that this will iterate through our job list to find and return the process ID of our current foreground job, if there is one, or 0 if there isn't. So when it comes time to actually implement, we can see the implementation for our stop signal handler is going to look very similar to our interrupt signal handler, right? We're going to go ahead and make that call to our foreground PID function. We're going to pass it to that global array, that jobs array that we have. It's going to return back to us a PID. That PID is either 0 or it's going to be the PID number. So we'll check if it's greater than 0, which means it exists, that job does exist. Then we're going to send that kill function. We're going to invoke that kill function on that PID, and we're going to go ahead and send it the the stop signal, which is an integer value. And then we're just going to return after that. Okay, so let me implement this along with you. So I'm going to jump into my code, and let me get into my handout. I'm going to go down to my T shell here. Perfect. And let's step through to where our handlers are at, which is going to be at the tail end of our functions that we have to implement. And let's see here. Okay, let's see here. This is right here. So you can see our current implementation is just a return statement. So let's go ahead and update this. So here I'm going to do PID T, PID, and then I'm going to call that helper function. And I'm going to pass in my jobs array. And then if the PID is greater than 0, then we're going to go ahead and call this kill function. And we're going to pass it in the PID, and then we're going to pass it in the STG, T, STP. Yeah, perfect. Oh, sorry, thank you. Thank you. SIG, TSTP. Perfect. Let's save that. So at this point, we're going to go ahead and send that signal. Now, our child process handler is going to have to be responsible for managing that signal, because that's one of the roles we said the child process handler is going to be responsible for. So I'm just going to go up here since we're already in our code base. We could already see, let's see right here. We have instances where when we exit out on a normal, when the process normally exits out, we delete that job from our job list. If we went ahead and have a signal process and terminate our job, we won't go ahead and do that here. So if we look at our signal child's handler, we're currently, let's see here. We handle the exited children already. That's what we saw here. That's this instance here. We handle the signal children. That's what this particular selection statement is evaluating. The new thing we're going to have to do is handle stop children. What are we going to do to handle stop children? That's the new signal we care about. Well, when a child process is stopped, we want the function to retrieve the corresponding job from the job list and update the state, because remember, we have our job list consists of a collection of jobs, and one of the attributes of our jobs is to have a state. And if we cause one of our jobs, one of our processes to stop, we should update its state to say, hey, it's been stopped. And then we want to print that information message to our shell, to our console. Yeah, so you can see here, actually, let me just jump. And reasons for change are obvious, right? We're sending this signal to a child process. We now have to be responsible for doing something in response to that, for managing, because our shell manages all the processes for us, right? So now we have to do something in response to that. So the key system functions, now I've highlighted the new ones, but I kept the collection of all of them that are inside of our SIG child handler. So if you see all this, what you're seeing is how we're growing this function out. So the new key system functions that we're going to be interested in is going to be our stopped, where we can evaluate true if the child process was stopped by delivery of a signal. And then we have this stop sig, which will return the number of the signal which caused the child to stop. So in our printout message, recall that we have a particular signal value, such as 20 or 2, and that's part of our print statement. And in fact, if we were to print that out inside of our signal handlers, that's the status signal that gets triggered. So we can always access that from our signal through the use of these calls here. And we'll take a look at that on the next slide. Then we'll also make use of 2 helper functions, a PID to JID. This is going to convert our process ID to a job ID, or return 0 if we can't find that process ID. And then to get a job PID. So this retrieves the job structure from the job list associated with a process ID. So again, I believe these are functions we might have used already, but I'm just highlighting we're going to use them again for this implementation. So just to take a quick look at the system functions that we're interested in. So notice we return, we as a parameter, we could pass in a status value. And so that's going to return back an integer. It's going to return a non-zero value if the child process is currently stopped. So again, this allows me to do a Boolean evaluation on whether the signal was stopped or not. And then here I can pass it in a integer value of the status. And so this will give back the signal number that caused the child process to stop, whether it was stopped or whether it was terminated or whatever. And then the helper functions, this is just the code, but all you really need to know, since it's already fully implemented, is that our getJobPID function searches an array of our job structures for a job with a specified PID. And if it doesn't exist, then it's going to give us back a null reference. And the PID to JID function iterates through the job list, searching for a matching PID and returns the associated job ID. Okay, with that said, the new implementation is going to be as such. Now, let's walk through, because now we're starting to get a little complicated with what's happening inside of the child process, and order is going to matter in these instances. So, just stepping through this function, and I'm going to highlight what are the new statements. We're going to create a variable to hold our child PID. We're going to create a status variable that we're going to pass in, and it'll get set by one of the functions that we can then evaluate to determine what the status of a particular process is. We're going to create a has next, that's our loop control variable, and we're going to set it to effectively true so that we can continually loop until we run out of child processes to evaluate. So while we have child processes, we will wait for a child process. And then we will check to make sure that it's greater than 0. This is our loop control variable. If we have another child process after this one, then we will have to do this repetition construct again. So all we're doing is updating our loop control variable right now, as opposed to the very end. Now, we're going to start doing some selections based off of the status of our child process. So we're going to see, recall, the system functions are kind of like truthy functions. They're like Boolean operations. We're going to find out if the status that is returned to us from this wait PID, right? This was the system function call we've done previously. That's going to update the value of status, and then we can use that status to find out if our child process was sent a stop signal or a terminate signal or an exit signal, right? Those are the three different states that a process could potentially have outside of just running if we're waiting for it. Okay, so if this returns true, then that means that this child process was sent a stop signal. So if that is the case, then we're going to go ahead and we're going to grab a reference to that job using the child PID that was returned to us from that function call. If that job exists, so if a job's returned, then I'm going to access the state attribute and I'm going to set it to be ST, which is short for stopped. So I'm going to update its status, its state, the job state. Then I'm going to print out a message that's going to match the message that the reference shell prints out. So, I mean, I can look at my my test, right? I see what message it prints out. I'm going to mock however that message is delivered to the console, to the shell. Okay, so if it's not stopped, so that's where my selection statement ends. If it's not stopped, then I'll go ahead and follow the rest of my logic. Well, then if it exited, I'm going to tell it to delete that job, which is already implemented. And if it was sent a signal, an interrupt signal, then I'm going to go ahead and delete that job. And if it was successful, I will go ahead and print out that message that that job was terminated. So recall these two selection statements that we're doing in response to prior signals we implemented in an earlier trace. But this is what we're implementing now for this trace. Okay, so let me jump on over here and actually implement this alongside you. Oh, I need to go down, actually. Right here, perfect. If okay, so we're going to say if and we're going to send it in that status variable. So if that's true, it's going to go ahead and be consistent, get job PID, and then we'll pass in jobs, and we'll pass in our child PID. Perfect. Okay, so once I do that, I'm then going to see if my job exists. So if it exists, then I want to go ahead and access its state attribute. And I want to set that to be stopped. And then I want to print out a message. And I'm going to do a flush print too, in response to the signal. So standard out is going to be my first argument, my stream. And then I'm going to do my string. So what was it? It was job. And then we'll have some integer value there. And then we'll have a set of parentheses and some integer value there. One will be my job ID. The other will be my process ID. And then I'll put stopped by signal. And then I will do the signal value, then a new line. And then here are the arguments I can put in here. I can do my PID to JID. So given a PID, I can get that job ID. And so here I'll pass it in the child PID. Oops. And then I have the child PID already, so I can just pass that. And then finally, I can do this call to translate this into my stop signal number. There we go. And we will just pass that our status value. Stretch this out so it all fits on one line. Okay. And so I have that. Let's go ahead and save that. And just out of curiosity, let's jump back over here. And yeah, let's see if I can go ahead and without making it into a nested multi-selection, just keeping it a set of single selections, I'm interested, will that go ahead and pass our test? Let's see. Let's whoops. So let's go here. This was a while since I filed. Okay, and now let's see here. Let's make test. This is 9 that we're currently on. So let's make up. So we have that. We have that. And it is just gonna hang there. Okay, which is good. So let's and okay, so let's say now if we update this with the multi-selection statement so that if it's stopped, we don't do anything else. Save that. Let's recompile. And now let's make that. No, does not look like it's the case. So now we have to do some fun troubleshooting. I tried using GE and let's take a look here. Let me take a quick gander. So if we're at, so here, if we take this, if this exists, we update stopped, we print this, and we check this, delete the job, check this, that's fine. We shouldn't have to. This looks fine. Everything looks. Yeah, I'll do this. It's that. Yeah, this. Oh yeah, thank you. No, I mean it does the same thing. Yeah, but you're right. I should be doing the process groups though. So I will. Let's just make sure. And we should also just double check here. So just make sure I'm doing the process group here. Well, yeah, that's right. And let's check if it's greater than, making sure that this is greater than 0. And here, yeah, process group there. And then here, yeah, that's fine. And we're checking the status here. We're checking to make sure this exists. And we update the state. Move that, yeah. Okay, let's go. Okay, let's take a look at this. So let's take a look at this. If we can't quickly, one of the problems sometimes with with live demos is sometimes they don't work the way you want. So let's take a look at what we have here. Something that we do know that works, just to make sure that we're not missing anything. So inside of our signal, this is the same, right? We check, do we have a child? Oh, oh yeah, this, I think. Oh. This I do remember now. I meant to introduce this and did I forget? Let us see if we forgot. Let's come back up here. Let's go here. Max have destroyed my ability to consider how I copy paste. Okay. Let's try this one more time. And then I'll have to make a note if this, okay, perfect. So the big thing that's missing, and I should make a note on this, is I meant to add this to the slide, and it's so easy to miss these things when you're turning these things into slides. So as we're sending our function call to our child process to get on our wait PID, we not just want to go ahead and look at no hang, but we also want to do a bitwise operator as a result to also untraced. Because that's the other condition we need to evaluate for a stopped process. And so I was going to motivate that, but look at what happens when I go to motivate, leave something out, and then forget about it myself when I go and make my slides. So actually, let me go here. Let's go back to the slides and update that. Look, it's not even in the slides, right? So W untraced. And let's go ahead and there we go. Because if we don't look for this particular status as well, obviously we're just going to hang indefinitely because we're never triggering, we're never getting back a child. So what this does is recall wait PID is going to give us back a child that has changed in some way. But if we don't give it all the conditions in which it might have changed, it just won't give back anything. And then we just lock up and stay in a way that does not allow us to finish that trace. Excellent. So has everyone else been able to actually get it working on their system with that change? Yeah. Perfect. Okay, so let's clear this. Okay, so just to make sure that I am complete with this particular trace, I'm going to run through and check, and I should get from trace 1, trace 2, trace 3, trace 4. I'm just going to start doing the makes because it's going to start getting a little lengthy to do this each time. Trace 6, trace 7, trace 8, and perfect. One more trace from 50% done. Let's see what happens here, and we can see we then fail. Okay, let's see why we're failing. Let's jump to the next trace. So in trace 10, if we examine the directives inside of this trace file, we can say this is going to process a new built-in command, the background command. So clearly we have an implemented background command. So we can see all these others we've seen before, starting the MySpin application for 4 seconds and as a background job. starting the MySpin operation as for 5 seconds as a foreground job, sleeping for 2 seconds. That's what the tester does. Sending a stop signal, then printing out the jobs, which we have implemented, but then this is the new function. We haven't seen bg. And then when we see %2 is giving a job ID. If it's just a number, then it's giving a process ID. So there's one of two ways that we can tell it a particular process to send to the background. So we need the ability to move our processes that are currently at the foreground to the background. That's the goal here. So now if I were to compare my output, I highlight it where the differences are. So a lot of what's nice is we're starting to get a deep enough implementation that a lot of our output matches our reference shell. But the line 6 and 8 here are going to respond back that there's no command, a command not found there. Let me see if that's actually what I get too, because I might have commented that out in a previous trace. Okay, so let me make sure I'm compiled, and let me do make test. Let me do reference test first, make sure that that is accurate. So here, this is 10. We get our echo, and yep, we get what looks like the output we looked at before. And now let me do, instead of the reference test, the test on my own shell. So here we can see, oh, I'm not even getting those command not found. So let me get congruent with the slides and go, let me see. I think I had, was that inside of my eval? So I believe I commented it out. If I didn't, I did not comment it out. I went ahead and so here it is. If our status is what is it? Is it greater than 0? I believe is the condition there. Do you remember? I believe it's greater than 0. I think if we get a non-zero value, then we want to do a print f. And what was the command not found? Perfect. Is there a period? Well, we'll see. Command not, oh, and bg. Okay, so no period, but it looks like there was a %s. And then probably a new line character. And then let's see here, that would have been our our argv at index 0. Okay, let's save this and see if I can't get myself back in line with the slides, because I'd hate to have an implementation that is different. So, okay. And let's go ahead and make that test 10. Let's see. Let's see if it's this way then. Perfect. So I get my background command not found. Perfect, perfect, perfect. Okay, so let us clear out of this and then start implementing this background function. So if we look in our built-in command, what we're currently doing is we get the command name, and then if it's quit, then we exit the program. If it's jobs, then we print the list of jobs and return a 1 to indicate that it was built-in command. If it's bg, then we want to invoke a other function that we have to implement ourselves. It's going to be the do bgfg function that's really going to be responsible for handling the background logic and pass it, and then we want to pass it our command line arguments. So if it's not any of that stuff, we're just going to return a 0 to indicate that was not a built-in command. So again, we're going to update our built-in command to offload this work to this other function, but this function is not implemented. So the implementation of this is easy. It looks like what we've been doing before, but what we're going to do is we're going to go ahead and we're going to send our argument vector over to this empty function, which we're going to move on and actually do something with in just a moment. So let me jump into my code here. Let's see here, which is out of curiosity. I should really look up the implementation. Okay, let's see here. I'm going to say it's just greater than, less than. But if it runs into issues, then we'll know where to debug. Okay, let me jump into my built-in command. So in our built-in command here, let's add a new selection statement. If we do a string compare, and our string commit compares between our command and the word bg, and if that is equal, if there's no difference between the two, then what we want to do is we want to call do bgfg, and we're going to send it our argument vector. And then we will also, after we're done that, return a 1 to indicate that that was a built-in command. Okay, save that. Just make sure we will compile. Clear this. Okay. Okay, so the next thing we need to do is actually implement the do background foreground process. So what are we going to have to do in just basic natural language? Well, we need to set up a pointer to reference a particular job. We need to set up pointers for our command and our parameter of the built-in command. I do that for readability. I always like my code to be as readable as possible. So I will add additional lines just to create variables that make the rest of my expressions more understandable. If the parameter provides a job ID in the form of a percentage sign and then some number, we will, which is our job ID, we would convert that into an integer with a to I. That's from ASCII to integer, a built-in function. We'll take a look at that in a moment, and retrieve the job using the helper function get job JIT. Now, if the command is a background job, we're going to send a continue signal, the sigcont, to the jobs process group ID and set the job state to be background, and then print the job details to the console. So again, we haven't implemented this function. When we go to this function, we'll see this function is going to be, I think, just a return statement. So everything's going to be new in it. So all new actions for this particular trace. And of course, the reason why we have to make this change is to allow us to make jobs either background jobs or foreground jobs. And it'll also allow us to signal a stop job to continue again. So some key functions you should be aware of. Well, we've seen some of the other signals. Here, we're going to look at the continue signal, or we could also think of that as an unpause if you were paused or stopped. So it's a process that has been stopped. So in the context of our job control, it's used to resume processes that were previously stopped using the sig stop. A to I, short for ASCII to integer, is a standard C library function used to convert a string to an integer. We've already seen the kill function, but again, it's a way of sending inter-process communication. And we've already seen the get job JIT function. So here, again, just like the other functions that are similar, we can go ahead and pass this to the kill function to send it as a particular status. A to I is pretty simple. We pass it a character pointer, and it will translate that into an integer value. It'll return an integer value if it represents an integer. And so here we're going to have a lot of code that we're going to have to put in here. It looks like a lot of code. It's not actually. Let's parse it out and just step through it initially. So here I'm going to create a variable to hold my job, and I'm going to default it. I'm going to initialize it to just be a null reference. Here I'm going to grab at element 0 from my argument vector. That's going to be the command, because I want to evaluate the command, presumably bg. And then bg can't be called on its own. It has to be given an argument, a parameter. So I'm going to save the parameter, which is going to be the next element in my argument vector. And that's either going to be a % sign and a number, which is my job ID, which is the only thing we're evaluating at this particular step, or it could be a process ID. Now, if I was really good, I would go ahead and implement both the process ID logic and the job ID logic simultaneously. But I'm only trying to pass this particular trace, so I'm going to do minimal implementation. So I'm going to check to see if my first character, this is a character string, right? So if the first character is indeed a % sign, then what I'm going to do is I'm going to grab the address of my first parameter, the parameter after the % sign, and I'm going to pass that to A to I. Remember, it requires a character pointer. It effectively takes a string or ASCII text and converts it into an integer data type. So I'm going to give it that address, and then I'm going to get back my job ID as an integer value. Once I have that, I'm going to be able to call the helper function, get job JID, pass it that global jobs list I have, pass it the JID as an integer value, and I should get back a job. Then once I have, so at that point, if that is successful, this is no longer null, right? This actually then has a value. If it does have a value, or it doesn't matter if it has value or not, I'm then going to move on and I'm going to see, is the command that was provided to us the bg command? If it is, because the reason why we're going to check this is that in a future trace, this do bgfg is responsible for not only moving processes to the background, but also moving background processes to the foreground. So that's going to be a future logic we're going to have to implement in some future trace. So on the instance of it being bg, where we take a foreground process and move it to the background, we're going to go ahead and issue that kill function. We're going to grab the PID from our job structure, and then we're going to send the sig cont, the continue signal, to that, and then we're going to access the state of our job, and we're going to change it to be a background job, and then we're going to print out the status. See, so it looks like a lot of code, but when we step through it, it all makes a fluent sense for exactly what we want to do for this particular trace. So let me go ahead and actually implement this here for myself. So what was this? This was inside of my do bg. So let me go here, do bgfg. So we can see that's where we are calling it in built-in command. And right here, it's currently just a return. So I'm going to now implement all the same things that I just told you about. So here, let's get our, so we have a struct job T pointer, and we will just call this our job process, job P, and we will set that to null. And then what we will do is we will have our character pointer. From our character pointer, I'll just call this command, and we'll grab argv, because when I clearly this technically optional, but to me, seeing CMD and param is a lot more readable than seeing argv0 and argv1. And then we will do argv. And the reason why I use param and not argument is because I have argv, an argument vector, and I don't want variable names that are too close. So I always try to find an alternate noun that represents the same thing if I already have a variable that's closely labeled so that it's not confusing. To give justification on some of that. Okay, so then once we do that, I'm going to check, okay, let's do the logic. What if my parameter is a job ID? If my parameter is a job ID, then I'm going to look at the first character in my parameter and see if it's equal to a percent sign. So if it is, then we know how to go ahead and grab that job using its job ID. I will go ahead and create that character pointer. We'll just call it J, and I'm going to grab the address from this character string of my param at index 1. So after the percent sign, which should now be a number, %2 is what's inside of our trace, right? Okay, so once I have that, shoot, why does it? Okay. Okay, so once I do that, I can okay, I can then, I'm expecting to get a integer in response to that. So we're going to call A to I, and we're going to pass in our J. And then once we have that, we can try to set the value of our job process, where we can get job JID. And here we will do jobs, and we will do JID. Okay, so once I have that, this should set this value here. So now I'm going to do another check if this is the background command. So if, and so here we'll do our string compare. We will do string compare with the command and bg. And if that has no difference, then what I want to do in response to that is I want to invoke the kill function. And from the kill function, I'm going to access my my job. And my job is going to have a PID attribute. So I'm going to send that to the kill function. And then also I need to tell it what is the signal associated that we're actually transmitting. It's the continue signal. Then the next thing I want to do is I want to go into my job and I want to access its state. And I want to change that to be a background job. And then what I want to do is I'm going to go ahead and then print that out. I'm just going to do printf. And let's see here. The print statement is going to be, what is it? It's a box notation. So there we go. %D, that's going to be probably my job ID, then my process ID. And then what we want to do is our command line. And then also we want to do, well, I think that's all we need. And then what we're going to do is job P to JID. Do I want to do new line? Let's see. I'll do new line. See if I want new line character. Okay, so we'll do that. We will do job P and access the PID. And then finally, we'll do job P and access the command line of our job structure. Okay, perfect. Let's just save that. And then let's test this out. Let me go here, compile. Let me go here and make this actually a string and not a character. Let's clear this. Okay, and now let's make test 10. No, I guess I don't need that new line character. Excellent. Okay. So now, just to make sure that this is on, we're getting points for it. We want to check, and let's see if we're getting if we're getting half of our points for this lab at this point. If we pass 10 traces, then we're at 20 points. Trace 7. Okay. Has anyone checked it already? Are you getting your points? Yeah. Perfect. Perfect. Trace 9. And finally, our trace 10. Yes. So now we're 50% of the way done. Let's move on. Trace 11. We should fail here. Yep. And we do fail at trace 11, which, why do we fail at trace 11? I'll let you have a guess. If we look at the directives in the tester, we can see it's calling the FG command. So clearly, once we start learning how to make a foreground process a background process, the next trace is going to challenge us to make a background process a foreground process. And that's exactly what we're going to do. And you could see it's using the same mechanism to use a job ID. So we're still going to defer at this point using the process IDs until some future trace. We know that's somewhere down the line. So just keep that in mind. So what we want to do here is clearly we want to implement the built-in FG command. So what do we have to do? If I actually do a printout, you see we're going to get these command not found, FG command not found. And because we're not finding that, notice the changes we're going to have here. So where here, let's see, this prints out, and then this is stopped by a signal, where that never happens because we're just doing command not found, and then it's still trying to run it. So it's never updating the status the way it should because we haven't implemented the functionality to affect the status. So that creates a domino effect in the printout statements between our reference test and our other test. So really what we have to do is we got to go to our built-in command process. We got to add in another string compare inside of there. We got to see if the command that was supplied was FG. And if it is, then we're also going to invoke that to do bgfg. Well, that's super simple, right? We don't even have to make a new entry. We could just do an OR on there. So let's do that. So I'm going to jump here. So I'm in this function. I already have a function that invokes bgf to bgfg. So I could almost just do a OR, paste, and change this to FG instead of BG. So if the command is a background command, a BG command, or a FG command, a foreground command, we're going to do bgfg and send it the argument vector. Okay, so what's the next thing we have to do? That was the easy part, right? So the next thing we have to do is, just like in the logic for our do bgfg, where we checked, is the command bg, and then we do something to make a foreground command act like a background command, we're going to see if the command is a FG command, and if it is, we need to make a background command act like a foreground command. So think about the nuanced difference between the two. So clearly the things that we're going to require for this implementation are all the same functions we used before, in prior traces. But the important one is, remember, in foreground processes that our process waits until that child process is done before we continue on. That's a big distinction between our background and foreground processes. So our logic is we're going to check to see if our command is FG. If it is, we're going to still send that kill command. I should do it to the process group. Remind me to edit that. Remember to put the minus sign in front of your PID. I don't know if I did that before, but I do want to do that. I want to update the state of my job to be a foreground job. And then instead of printing out the state, I'm just going to wait FG, which we already implemented before, because that's what we do for foreground jobs. Okay, with that said, let's actually do it. So here we did that. So inside of here, we can see, I'll start by just copying this. So here, if my command is an FG command, I'm going to update this. I want to do process groups. Notice it works with just the process ID and not the process group ID, but it's gonna help us with some traces in the future. And I haven't made those slides because I started making them with the minus sign already with the process group ID. I'm going to update the state to a foreground job instead of printing out. So instead of doing this, I said that I was going to wait. And here I'm going to pass it the PID from my job process. Let's save that. And actually, let's do this. Let's check the status. So let's clear this. I'm going to say after I do that, just to show the slides say we should check our output. So let's make test 11. Is this 11? Let me make sure I compile. It's important to compile. Yeah, this is test 11. Okay, yeah, that looks like the output that I got with my reference test, right? Yeah, that looks the same. So let's do this. Oops. And let's just momentarily run through and just verify that we're getting our 2 points so that we can move on. And in fact, I think you're going to see something interesting here. While this runs in the background, I'm going to jump over to my slide deck. And we're going to see that this trace here, trace 12, uses our tiny shell to forward an interrupt signal to every foreground process group. Since we have been prefacing, whenever we use the kill function, we've been putting a negative sign in front of our process ID, right? If we just do the positive sign, like I've done earlier today, that works. But that only works for that one process. If I put a negative sign, it allows the system to know, kill all those processes in that group. So we should, because we've been using the negative sign, we should automatically get through 12. We're compliant with that. In fact, 13 checks to see if we can kill all the signals. So 12 sees if we can kill all the processes inside of our interrupt signal handler. 13 sees if we can kill all the processes, our foreground processes, inside of the stop signal handler. And 14 is going to check to see if we're killing all the processes inside of our do background foreground. So every time we're calling the kill function, if we at least put the negative sign in front of the PID, that's going to get you through 12, 13, and 14. Which means, let's go back over here. If I look at the points I have, I'm up to trace 15 now. So we are now 75% of the done. It was done with shell lab. But the important aspect, and I'm going to change these slides if I were to do this again, so that I fail on 12, 13, and 14, where I have to go in and put a negative sign in front of my call to my kill function to illustrate that that's what's going to make those pass. But because we did that, so I just want to make sure everyone understands why we passed those. Okay, so I'll leave you all off on what we will talk about next time. There's only 5 traces left. These slides are available to you right now. These slides will get you all the way up to trace 18. The only ones that are missing off the slide deck are the redirects. So the next thing we will be looking at will be the error handling. That's the thing I kept kicking off, right? The thing that I kept booting off to the side was, we'll make it work. We'll make it work. We don't care about faulty input. We don't care if the user supplies us with something we don't want, right? Well, guess what? In the real world, you want to build something that's fault tolerant. You need to respond if something was put in error. So the next trace will focus on doing the on check error handling, simple error handling, to make sure we've been catching those easy to catch things. So you can see what this directive is nothing but a lot of bad input. We'll look at that next lecture, or you can look at it ahead of time through the slide decks and move along. But that's going to be our lecture today. This will be fun to go through and re-edit and make some corrections so that we can get through all these bad inputs, but I'll also reiterate what we want to do starting next lecture as well. Okay, does anyone have any questions? Well, then I will see you all on Thursday. Oh. Yeah, so the videos I have, so I had a question, when will the videos be posted? I have just downloaded all the videos and made everything I need to go ahead and upload them. So we'll upload them tonight now. And just like, it was my intent to try to get them up when the slides were up, but it's just been too busy. So I have them primed, I just have to upload. So look out for those. They should be up later this evening. Yes.